Hi guys, hi everybody. Welcome to the class. My name is Madhu Kashyap. I'm a physics educator at an academy. I'm an astrophysicist from Bengaluru. I'm a young scientist awardee from Indian Science Congress and a young researcher awardee from European Space Agency, Netherlands. Guys, here are some of the very interesting concepts what we studied in the previous class. Before that, let me just quickly check whether the link is available for you guys. Let me quickly do this. Okay, so I think I can share it with you guys right now. Let me just share it in the group. Okay, here it is. Okay, I hope you guys can see me now. Okay, I really think you guys will be able to write things in the chat box. Let me quickly say hi to everybody publicly. Hi all. So I know you guys are joining in right now. You're getting the link now, so it may take few seconds to join in the class. Okay, so let's get started. Sorry for 5 minutes delay. Last class we did study these interesting aspects on physical properties of star. So where we try to understand. Let me quickly put my pen tab right away. Let me go ahead and put the pen tab. And where's my pen? Okay, all right. So let's get started. I think I need some help with the power pad here. Okay. Pointer options. Okay, so hi astrophile. Hi, hello. You're the first person to be joined today. Okay, or you're the first person to say hello to me in the chat box. Welcome to the class. So in the last class, in the very first class, so this is class 2 of Astronomy Olympiad and NSEA preparation examinations. Guess your name. Hi, good evening. So people are joining in, so on, slow and steady wins the race. Is your name Varnika? I don't know what's your real name, astrophile. Okay, so class 2. So in the first class, the stellar properties of physics. Oh, you're Om. Hi, Omji. So when we talk about class 2, we in the last class we started physical properties like luminosity, brightness, all those things. If you have not watched, so look at the similar description with class 1 title, so you will be able to go and look at those recordings in the previous class. Hello, good and verified cryptos airports. Hi. So now what we are gonna do in class 2 is we are gonna continue the topic with respect to distance. So I'm gonna tell you a method called as parallax method, which you would have studied in your class 11 in detail. Parallax method. So it's one of the easiest way to understand how to measure distance using basic trigonometry knowledge. Okay, let me just quickly keep my things in order. Okay, just a second. Give me a second. I always ask for seconds, no, guys? Okay, yeah, totally, yeah. Parallax method. So it's also called a stellar parallax, trigonometric parallax. There are different names in which we call this parallax. So we have something called as trigonometric parallax, and or we can call it as stellar parallax. So same thing with different terminologies. Okay, stellar parallax. So in these techniques, in these methods, we consider heliocentric model. You guys remember geocentric and heliocentric models, right? Geocentric is where Earth is kept at the center and everything revolved around the sun, around the Earth. That was the idea of geocentric. In heliocentric, we know helio was sun was at the center and everything moved around the sun. So when we talk about this particular technique, we have to draw this particular diagram. Okay, so there is sun here, sun is here. Okay, and we have the orbit here. So in this orbit we have Earth, say this is Earth in December. In December, this is the position of Earth, and this is Earth in June. Say it's in June. During the time of June, the Earth is located here in June. Okay, and there is a star here. Okay, I'm just drawing this star like this because we all used to do star diagrams like this. Okay, yeah. So in this particular, if you want to find the distance between the sun and the star, say let us call that distance as d. This is the distance we are trying to measure, d. What you do is you apply, and we know what is the distance between sun and earth. Let's call that as a. A is the distance between earth and sun. And if you make it as a triangle, and there are background stars, so we can extend it there. And from here, this will be an angle subtended. Okay, so this angle will be called as parallax angle, or you can extend this, call this as also parallax angles using basic geometry, right? So we know P here is called as parallax. P is parallax, and d is the distance of the star. D is the distance of star, and A is 1 astronomical unit. The distance between Earth and Sun is 1 astronomical unit, which is 1.5 into 10 power 11 meters. Okay, array yaar, why does this line keeps appearing? Eraser. Okay, so let me go back to pointer options. So this is the diagram in which we try to find the distance of this particular star from the sun. So it is given from figure. I can just directly write from this figure. If I have to find P, I take the tan theta of it. So tan P will be equal to A by D. Tan P will be equal to A by D. Since this angle is very small angle, we are talking in the sky, very few. So this tan P is very small. So since this parallax angle is small, tan P will be approximately equal to P. Tan P will be approximately equal to P. So P will be equal to A by D. Okay. So parallax is basically the ratio of the distance between Earth and Sun divided by the distance of the star. Okay, this is, yeah, tangent, exactly, astrophile. So this is basically the tangent we are talking about. And how do we convert this into arc second? So when we look at the sky, we should use the language. We should not say meter, centimeter and all. You should be able to say like a clock face, like degrees, minutes, arc. We say degrees, arc minute, arc second, because we measure them in arc minutes and arc seconds. So that's the reason we are gonna do that. Okay, I need to add some slides. Let me keep this real quick. Let me add some blank slides. Okay, so this should do the trick. Let me go back to the full screen mode. Okay, so pointer options. Okay, so here since we found P is equal to A by D as the formula, parallax was equal to A by D. If I have to convert into arc seconds, what I have to do is I have to multiply with a very special number, this number 206265. So when I multiply with this 206265, it gets converted into arc seconds. Okay, this is how we are gonna find the distance in arc seconds, like the parallax in arc seconds. And you know, if P is equal to 1 arc second, if you take example, parallax is equal to 1 arc second, what does it mean? 1 arc second means, so D will be equal to, we know this, A is equal to 1 AU, we know 1 astronomical unit, we know already 1 AU. Okay, so D will be equal to 206265 AU, right? So distance D will become this much, and 1 AU, we know 1 AU is 1.5 into 10 power 11 meters, right? So if I do this multiplication of 206265 into 1.5 into 10 power 11 meters, when I multiply these two, I'm gonna get this number 3.08 into 10 power 16 meter, Okay, so this is nothing but 3.26 light years. Okay, light years I can write it as Ly, light years. So 3.26 light year is nothing but 1 parsec. 1 parsec, or I can just write it as 1 pc, small p and small c. So that is the SI unit of parsec. So this is one of the ways to measure the distance in parsec. Okay, so this is one of the important tools in understanding the distance. Okay, now we are going to move on to the next topic, which is called as surface temperature of the star. Surface temperature of the star. Surface temperature of the star. Okay, so how do we understand the surface temperature of the star? So so Om Naranji is one of the persons who is paying more attention here. So let us look at what is the surface temperature of the star. Where are others? Others are still yet to get the link. Yeah, I know my student group is huge. Where are they? I don't know where they are. Maybe they will look at the recordings, because the the link started five minutes late. I think that's the reason people have not got the link. I think, yeah, it's an exciting topic, surface temperature of the star. How do you find the temperature, surface temperature of a star? So we use a black body. We use a black body technique. Okay. So you guys know what is a black body. In quantum mechanics we would have learned what is black body radiation in detail. So where Wayne's law tried to explain and failed, and then came Stephen's law, which failed, then Rayleigh-Jean's law, which failed, and finally Planck's law comes to our rescue to explain the entire curves of the black body radiation, right? So basically it's dependent on the black body, whose luminosity is same as the star. So it gives that relationship. Okay, surface temperature of a star is the temperature of a black body whose luminosity is the same as that of a star. So that's the reason we say black body is a very key thing to understand the surface temperature of the star. So we also, in order to measure surface temperature, we use a powerful tool called color. We use a powerful color technique. So we have something called as color of a star. How do you find a color of the star, and how the color of the star is related to the surface temperature numbers? See, color is related to the numbers. So cool, right? So imagine a hottest star. Imagine a hottest star. Roughly the temperature, we can take one rough temperature of around 28,000 Kelvin. 28,000 Kelvin, and then we will take and what will be the color of this hot star? It will be blue in color. It will be blue color. And our sun, let us take the in between intermediate star, intermediate hot star, sun, as example. Okay, sun is approximately 5800 Kelvin. This is the surface temperature of the star, and our sun color will be yellow. Our sun's color is yellow. And if you take a colder star, okay, of order approximately 2500 Kelvin. Okay, so if you take this cold, I should not write colder, cooler will be better word. Colder doesn't sound poetic. Anyway, let me write that it as cooler. Okay, pointer, where are you? Let me say it as, oh, my pen, my pen is made in China, so sometimes it doesn't work properly. Cooler star is 2500 Kelvin. And what will be the color? Any guesses? What might be the color of this cooler star? So we saw blue color, we saw yellow color. What could be this color? Any guesses? What could be the color of this star? Any guesses? Anybody can answer this. Okay, cooler star will be red in color. Yeah, it will be red color. So this will be blue color, this will be yellow, and this will be red in color. So this is how the different hot stars are differentiated. Okay, so in order to understand how do we look at these colors and all these things, we use to determine the surface temperature of the stars using colors. We have a technique called as CCD technique. Okay, let me go to the next slide. We have a technique called as CCD. We use CCD cameras to look at these colors. Okay, so what are these CCD cameras? You know, CCD is charge coupled device, right? Charge coupled device. We use something called as UBV filters. UBV filters. So what does this U, B and V stands for? So when we use U filter, what happens is when this is transparent. This is transparent to ultraviolet radiation. Transparent to ultraviolet radiation. This is for U filter. Then you talk about B filter. B filter, it is transparent to blue light. Okay, it is transparent to blue wavelength. I should not say blue light, blue wavelength will be the right word. Blue wavelength. And when we talk about V filter, it is transparent to visible wavelength band. You know waveguide, right? Visible wavelength band. Arey yaar, my pen. Okay, visible wavelength band. Okay, so this is how yeah, correct, you guys are getting along with me. Good. So we can take the brightness of each star, B, this as BU, and this as BB, and this as BB. So these are the corresponding brightness that is connected to this filter. Okay, so with this ideology we do something called as color ratio. We understand a concept called as color ratio. Okay, for sun we can take as an example and look at this color ratio for sun, for our sun. For everything we take example as our sun, because if you apply for sun, then we can apply for other stuff. Pen needs some orange juice. My pen needs all types of juices, people. So yeah, let us say this is the graph of our sun. So what happens is, in order to find color ratio, let us take color ratio here. Color ratio basically means we are taking BV by BB for sun, visible light and blue wavelength. Okay, and this is the surface temperature. Surface temperature. Okay, so let us say we have a curve like this. Okay, like this kind of a curve, and let us mark some numbers: 0.5, 1, 1.5. We are gonna put some numbers to understand this. 2, and so on, 2.5, and so on and so forth. Okay, so here also we are gonna give some numbers: 3000 Kelvin, because this is surface temperature, I'm taking in Kelvin. 3000, then I should write it a little higher because my graph is a little lower here. Or let me fix this graph. Where is my eraser? Okay, let me redraw this line so that it fits the numbers I'm trying to point out here. Okay, this should do that trick. So this is around 6000 Kelvin, this is 9000, then you can put like 12,000, and if you can go ahead with it. Okay, but I am interested for our sun. So our sun will come around here 1.5, okay, somewhere here, and this corresponding line, when you draw a perpendicular, it will reach somewhere. Maybe my line is not so neat. Maybe here should be the right line. Okay, so yeah, somewhere close. So this number is corresponding to 5800 Kelvin. Okay, so that's the idea behind this. Where is my eraser? Let me try to draw it as much as possible. Okay, I want to draw it neatly. That is the point here. Yeah, close to 5800 Kelvin. So this is our sun. This will be our sun. So from color ratio, I think this is not 1.77. That is the right number. Yeah, 1.77. I should be drawing that correctly. Yeah. My drawing skills are bad when it comes. The axis. Sorry. Okay, let me redraw that. Where are you, Mr. Axis? So yeah, somewhere here, somewhere in 1.77. So 1.77, which is the ratio BB by BB ratio for our sun, color ratio sun for our sun. This corresponds to, in this graph, when you plot this graph against the surface temperature, it will correspond to around 5800 Kelvin, which is the surface temperature of our sun. This is one of the techniques to measure the surface temperature of our sun. And you might be wondering how this thing comes into play. This works with Wien's displacement law, Wien's law, so which you have studied in lower classes. So lambda T is equal to a constant. Okay, so how wavelength and temperature can be related for our sun. Even using Wien's law, if I try to understand from wavelength how do we find the temperature, if I have to find by knowing, if you take a spectra of our sun and you know the wavelength of our sun, and if you want to find the corresponding temperature, so the maximum peak, wavelength peak, will be around 5.5 into 10 power minus 7 meter. Okay, so let me put that 5 into 10 power minus 7 into temperature T, and the constant, Wien's constant, will be 0.0029, right? So this temperature will come around 5800 Kelvin. Okay, this is for our sun. So from wavelength, how do we find, and from color ratio, how do we find the surface temperature? These are the techniques used. Okay, yes, all right. That's good. So we understood the surface temperature of the stars. Now one of the important physical properties is size. How do we find the size of the star, or radius, size or radius of the star? Size of the star. So yesterday we studied luminosity, right? Luminosity is if there is this surface area, how much energy flux is coming out of a unit area in unit time. So energy into area, E into A, right? And this energy is nothing but how much energy is coming in that area. Energy is given by Stephen's law, sigma T power 4, and area will be 4 pi r squared. So L will be equal to 4 pi r squared sigma T power 4. This will be the luminosity equation. Okay, this is the luminosity equation, which I did not write in the previous class. I just defined it. So here is the equation for luminosity. And how do we find the corresponding size? Just rearrange for r squared. R squared will be equal to L by 4 pi sigma T power 4, and r will be equal to square root of L by 4 pi sigma T power 4, right? So this is basically the formula to find the radius or the size of a star, size or radius of the star. Okay, so and also if you want to take one example of finding the radius of our sun, so how do we find the radius of our sun? Radius of our sun will be equal to luminosity of the sun divided by 4 pi sigma. Sigma is Stephen's constant, and the surface temperature of the sun whole power 4. And don't forget the square root, so I'm writing it as whole power half. Okay, so luminosity of our sun is 3.9 into 10 power 26 divided by 4 pi. Stephen's constant is 5.67 into 10 power minus 8, and the surface temperature of our sun approximately is 5800 Kelvin. So this entire thing whole power half. Okay, so when you do the simplification and yeah, press your calculator basically, so 695,500 kilometer, this is what will be the radius of our sun. Okay, this is one of the examples for our sun. For sun, this will be the radius. All right, yeah. Now going to the classification of the stars. So if there are these stars right in the sky, or just like sun rising and setting, all the stars, all the constellations rise and set except for one star which is called as pole star. Pole star is basically showing you the direction of north. Pole star is one star which does not rise or set like other stars. Okay, so it basically shows you the direction north. So if you are in the sea and if you don't have the sun and only stars are there for your rescue, and if you don't have a compass, so in order to find the direction north, south, east, west, I think pole star will be one of the stars which does not move. That will be the north star. Okay, it's also called as north star. So with this ideology, so people had to do classification of stars. Okay, so classification of stars. How are these stars classified? So we have a code to remember this. So we have O, B, A, F, G, K and M. So how do we remember this? So this is basically the hot stars. Okay, these are hot star. And G type star, our sun is a G type star, and M is a cooler star, cold stars. Okay, cooler star will be the right word, cool star. Yeah, that will be all right kind of thing. And keep on writing cold, I don't know why. This will be a cooler star. Where is my pen here? Okay, this will be cooler star. This is our sun, and these are hot stars. So hot and massive stars, and especially these are fast rotators too. OBA are fast rotators too. And how do we remember this? Oh boy, a fine girl kiss me. So this is for O type, B is for B type, A is for A, F is for fine is for F, G is for G type, K for kiss, M for M. So this is how we remember. Okay, or you can if you're a girl, you can say, oh boy, a fine guy kiss me. Okay, if you prefer a guy or girl, it's completely left to you. Okay, so this is how we remember this particular sequence. So this will be the hot stars and this will be the cold stars. This is called as classification of stars. We will look at what are the stellar lines, spectral lines corresponding to this OB, AF, GKM in the upcoming classes, and also we will talk about the mass of the star. How important the mass binary interaction of the stars looks like, and also we will look at the coordinate systems, like how these celestial coordinate systems work. Okay, so how are they connected to each other, and especially in the positional astronomy, like latitudes and longitude, we use something called as RA and dec, right, ascension and declination. All these things we are going to study in the next week's session, which is on Friday. Okay, which is Friday. Every Friday, Saturday around 10 p.m. I'll be coming live. Okay, if you guys like this kind of videos, I want you to give a like and hit the subscribe, the bell icon to make the YouTube algorithm happy, so that you get all this content for free. So we'll make sure we are going to continue it, and I actually teach at an academy. So if you want to learn more of these courses with an app and with proper settings and all those things, I think you should go for an academy, and you can use my referral code MD. The famous MDH advertisement, right? Similarly, MDK. So if you use MDK10, so I will, you will get a when you are taking a subscription and you use this subscription code, this referral code, you will get the discount required. Okay, so sometimes if there is an offer running, you will get more than 10%. If normal days, you will usually get 10% off on the current subscription price. So wherever an academy app asks for a referral code, online or offline, you can use this MDK10. Okay, so with this, owner NG has some comments above. Your comments above. GJ667cc needed information, curiosity. Okay, I work on exoplanets. So exoplanets are planets outside the solar system, and there are some habitable planets. If the planet is too close to the sun, it's too hot. If the planet is too far away from its star, it is too cold. But for Earth-like planet, the distance was just right to sustain water and host life. So in order to look at these habitable zones in these kind of things, we go in the exoplanetary direction. So when we look at them, there are some habitable planets, and one of my favorite habitable exoplanet is GJ667cc. So the GJ667c is the name of the star, and another subscript C is the alphabets are basically giving you the orbits. A orbit, B orbit, C orbit, and so on and so forth. So the name of the star and the host star. Since our paper, me and my team, we worked on exoplanets and habitability, and this had a very high habitable score for we Earth similarity index for finding a twin Earth similar to Earth, twin Earth. I think this had a very high probability with respect to Earth similarity index, which is available in Astrophysics and Space Science Journal, which became the cover page when in the year 2017 or 18, I don't remember exactly. You can go and check both the editions. Which became the cover page. It was authored by me and my team. So and we also found the way to a technique to find surface temperature of those exoplanets too in the paper, and we also found mass similarity index to find mass-like planets in the system. So these are the things that we looked into in this context, and this is the extra information I wanted to share with you in today's class. Tomorrow we are gonna continue. Not tomorrow, I mean the next Friday. We are gonna continue at 10 p.m. Until then, have a nice day. If I am late by 5 minutes or so, kindly forgive me because I am new to OBS. I am using OBS to stream online, so it may take 5 or 10 minutes sometimes to get logged in. So until then, have a nice day. See you in the next class, and don't forget to share this video. Thank you and good night.